Tom Whitmore's fingers traced the stamped numbers in the cast iron column, feeling the sharp edges where a factory worker had driven steel dies into hot metal 94 years ago. Serial 24487, Cincinnati Milling Machine Company, 1931. The machine hummed beneath his palm, spindle turning at 480 RPM as carbide inserts carved through aluminum plate that would become a prototype die for an electric vehicle manufacturer. Chips curled away in silver ribbons, falling into coolant that pooled around a table older than the invention of television. Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old machines' legacies alive. The contradiction filled the 20 by 30 shop bay like a physical presence. Along the north wall stood 3 modern CNCs, their sheet metal enclosures gleaming under LED fixtures, touchscreens dark in standby mode. But here in the center, anchored to concrete poured when Herbert Hoover was president, sat 4,200 pounds of American iron that had never stopped earning money. No computer interface, no digital readouts. Just hand wheels worn smooth by generations of machinists and ways hand-scraped to precision that held true when Harry Truman occupied the White House. Dr. Sarah Chen adjusted her glasses and leaned closer to examine the wear patterns on the table's surface. The industrial historian had driven from Northwestern University specifically to document this machine, one of perhaps 12 Cincinnati No. 2 Universal Mills still in daily production anywhere in the country. She had seen museum pieces, carefully preserved antiques behind velvet ropes. But a machine cutting actual parts for actual customers in 2025? That was rare enough to warrant academic investigation. Tom shut down the spindle and wiped his hands on a rag that had absorbed 30 years of cutting oil. His great-grandfather Frederick had bought this machine in March 1931 for $1,147, paid in installments over 18 months while the Great Depression crushed manufacturing across Milwaukee. The purchase receipt still existed, tucked into a leather-bound logbook that documented every oil change, every bearing replacement, every job run on this specific machine for 94 uninterrupted years. 3 generations of handwriting filled those pages, a continuous record of maintenance and care that read like a family Bible. The machine currently generated $180,000 in annual revenue. Operating costs ran $22,000 per year for electricity, tooling, and maintenance. Pure profit margin that no modern equipment could match because there was no loan payment, no depreciation schedule, no planned obsolescence timeline forcing replacement every decade. Tom had calculated the numbers obsessively, preparing for the argument he knew was coming. His son David wanted it scrapped. 29 years old, engineering degree from Milwaukee School of Engineering, fluent in CAM software and parametric design. David saw a museum piece occupying 120 square feet of valuable floor space. He saw a liability, a machine without part support or factory service, a relic that couldn't compete with 5-axis simultaneous machining or lights-out automation. He had already sent Tom links to new equipment, payment plans that promised productivity improvements of 400%. But David had never opened the logbook, had never read his great-great-grandfather's first entry, written in careful cursive with a fountain pen. Purchased Cincinnati No. 2, Serial 24487, $1,147. This machine will outlast me if I care for it properly. Frederick Whitmore had been dead for 43 years. His machine was still making the parts that fed Tom's family. Dr. Chen photographed the paint archaeology visible where millions of chips had worn through layers of industrial coating, battleship gray underneath current blue. Olive drab beneath that from war production years when this machine ran 24-hour shifts making bomb fuse components. Each layer told a story of survival through technological epochs that should have rendered it obsolete. The CNC revolution, computer-aided manufacturing, digital controls, Industry 4.0. Every wave of innovation had declared manual machines dead. Yet, Serial 24487 kept cutting metal to specification. Tom pulled the current job traveler from his clipboard and showed Chen the economics. The prototype die would take 14 hours of machine time. He had quoted the customer $4,200. Competing shops with modern CNCs had quoted $6,800 because their programming time exceeded their cutting time. The Cincinnati's simplicity had become its competitive advantage, a reversal of technological logic that seemed impossible until you watched the numbers. But the real question, the one that made Tom's chest tighten every time David mentioned 5-axis machining centers, wasn't about money. It was about something harder to quantify. When you scrapped this machine, where did 94 years of accumulated knowledge go? Bernard Kowalski, the shop's senior machinist, had run this specific Cincinnati for 31 years. He knew its tendencies, its quirks, the exact feel of the hand wheel when a tool was deflecting or a setup was fighting the cut. That knowledge wasn't written in any manual. It lived in practiced hands and couldn't be transferred to a new machine any more than you could transplant muscle memory. Chen asked the question that framed everything. In an industry where equipment cycles every 10 to 15 years, how did one machine survive 4 generations? Tom smiled and walked toward the machine, running his hand along the column's flank like you'd pat an old dog. Outside the shop windows, January snow fell on Milwaukee streets where Frederick Whitmore had walked in 1931 carrying the burden of Depression-era debt and the hope that American iron built heavy enough would outlast the economic catastrophe destroying his industry. The machine had survived because Frederick understood something that modern manufacturing had forgotten, but proving that to the 5th generation, that would require going back to the beginning, to the engineering philosophy that made survival possible in the first place. March 1931. The crate arrived at Milwaukee's freight depot on a flatbed rail car, 10 feet of wooden planking protecting 4,200 pounds of machinery packed in Cosmoline thick enough to seal out moisture for a transatlantic voyage. Frederick Whitmore and 2 helpers spent 3 days uncrating, positioning, and tramming the machine to within 0.02 of an inch level in both axes. The installation manual that accompanied the Cincinnati ran 50 pages of dense technical prose, every specification documented with the assumption that the buyer would need to maintain this equipment for decades, perhaps generations. Tom laid the same manual on the machine's table, its pages now translucent with oil stains that mapped 80 years of reference. Every tolerance, every bearing clearance, every assembly procedure remained identical to the day Cincinnati Milling Machine Company had typeset the pages. The manual expected infinite service life, a philosophy so foreign to modern manufacturing that Chen initially mistook it for marketing exaggeration. But the proof stood before her, still cutting metal to the specifications printed in 1931. The casting itself revealed the engineering philosophy that made longevity possible. Cincinnati had poured the column and base as a single piece of meionite cast iron, a specialized alloy with controlled graphite structure that would dampen vibration for as long as the iron existed. But the critical step came next. They aged the casting for 6 months in the factory yard, allowing internal stresses from the cooling process to dissipate naturally through seasonal temperature cycles. Tom explained that modern foundries stress-relieved castings in ovens over 48 hours, faster and cheaper, but the molecular structure never achieved the same stability. When Cincinnati finally machined the aged casting, they hand-scraped the ways rather than grinding them smooth. Tom demonstrated the principle using Prussian blue dye on a precision straight edge, running it across the table's surface to reveal the contact pattern beneath. Blue marks formed a random constellation where high points touched the reference surface, each spot indicating a bearing area that would distribute cutting loads across the ways. A master scraper at the Cincinnati factory had created these contact points in 1931, working until the surface showed 20 points per square inch, enough to spread forces evenly while maintaining the microscopic valleys that held lubricant. Chen knelt beside the table and examined the scraped surface under magnification. The oil pocket still functioned after 94 years of continuous operation, tiny reservoirs feeding lubricant to moving surfaces that had traveled millions of linear feet. Tom measured the wear using precision gauge blocks and indicators, 3 ten-thousandths of an inch on surfaces designed to hold 5 ten-thousandths when new. The geometry had degraded less than 1/10 of 1% across nearly a century of production cutting. Frederick Geyer, the Cincinnati engineer who had overseen the number 2's development, built his reputation on a single principle that Tom quoted from a 1928 technical paper preserved in the shop's files: accuracy through geometry, longevity through documentation. Every component in the machine carried a part number. Every replacement bearing, every gear, every tiny spring had been cataloged with military precision. Cincinnati kept those parts in production for over 50 years, understanding that a machine tool was an investment that should outlive its builder. The economics of 1931 made this philosophy inevitable. Cast iron cost relatively little, but skilled labor commanded premium wages even during the Depression. Cincinnati's strategy invested heavily in material mass to minimize lifetime labor costs. The 4,200 pounds of meionite wasn't excess. It was insurance against deflection, vibration, and the repair cycles that destroyed profitability. Frederick Whitmore had paid $1,147 for a machine engineered to deliver $50,000 of lifetime value, though neither he nor Cincinnati's sales representative could have predicted it would still be earning money in 2025. December 1942, the shop converted to war production in less than a week. The Cincinnati began running 24-hour shifts, making bomb fuse components, precision brass parts measured in 10,000ths of an inch that would detonate explosives over German and Japanese targets. Frederick hired women machinists to replace the men who had deployed overseas. The machine ran continuously for 38 months, accumulating over 27,000 hours without shutdown, a stress test that should have destroyed equipment built for peacetime production. Tom pulled a photograph from the archive box, its edges curled with age. His grandfather stood at the Cincinnati in 1943, 16 years old, surrounded by 3 women war workers. Chips covered the table. Coolant pooled on the floor, but the machine ran, its spindle turning with the same steady hum that filled the shop in 2025. The logbook from that period documented brutal treatment that would horrify modern maintenance engineers. Operators forgot to oil the ways. Cutting tools dulled beyond specification before replacement. Material shortages forced the use of substitute lubricants never intended for precision machinery. Yet the machine absorbed this abuse through fundamental design principles that Frederick Geyer had understood in 1928. The 4,200-pound mass acted as a thermal sink. While the cutting zone reached temperatures that could boil water, the machine's core temperature rose only 8 degrees Fahrenheit. Modern lightweight machines experienced dimensional changes that destroyed accuracy under continuous operation. The Cincinnati's mass simply swallowed the heat and maintained geometry. Chen examined a logbook entry from August 1944, written in careful feminine script. Ran dry for 6 hours. Oil pump failed on night shift. Bernard Klein inspected ways this morning, no damage found. The scraped surfaces had retained enough lubricant in their microscopic pockets to prevent galling, even when the manual oiler stopped functioning. Tom noted that ground ways mirror smooth and apparently more precise would have seized under the same conditions. The old craftsman who had scraped this machine understood that apparent roughness created functional superiority. The statistical proof appeared in production records that Frederick had maintained throughout the war. The Cincinnati produced 847,000 fuse components between 1942 and 1945. Rejection rate measured 0.03%. The accuracy established by hand scraping in 1931 held under the most brutal production conditions imaginable, validated by military inspectors who measured every 100th part with precision gauges that detected variations invisible to the human eye. The Korean War in 1951 presented a different challenge. The military wanted complex aircraft components requiring 5-axis coordination. The Cincinnati remained a 3-axis manual machine, apparently obsolete for the new requirements. But Frederick's solution revealed the machine's true value. Rather than replace it, he designed elaborate fixtures and rotary tables that mounted on the Cincinnati's table, giving it capabilities its original builders never imagined. Tom showed Chen a fixture from 1952, a mechanical marvel of compound angles and indexing mechanisms that transformed the machine's rigid, precise geometry into a platform for unlimited adaptation. Modern machines were optimized for specific tasks, designed around narrow performance requirements that made them efficient but inflexible. The Cincinnati had been optimized to be a stable reference plane, a foundation of proven accuracy on which anything could be built. That fundamental difference explained how it survived technological revolutions that killed its contemporaries. The machine didn't resist change. It accommodated change while maintaining the geometric relationships that made precision possible in the first place. September 1978. Tom's father James returned from the International Manufacturing Technology Show in Chicago and stared at the Cincinnati with new eyes. He had walked aisles of gleaming CNC machines promising productivity improvements of 400%, FANUC controls that remembered tool offsets, automatic tool changers that switched cutters in seconds, lights-out manufacturing that ran through the night without human operators. The future had arrived, and it made 47-year-old cast iron look like a museum piece. The family meeting lasted 3 hours. James proposed scrapping the Cincinnati and taking an $85,000 loan for a Mazak CNC. Competitors were winning contracts with promises of faster delivery. The shop was losing ground to operations that had embraced computerized machining, but Tom's grandfather, Frederick's son, now 51 and serving as shop foreman, argued against the change with numbers that couldn't be dismissed. The Cincinnati had paid off its loan in 1936. It had generated pure profit for 42 consecutive years. Why trade profit for debt? The recession of 1982 nearly ended the debate permanently. Revenue dropped 60% as major contracts migrated to CNC-equipped competitors. James listed the machine in trade magazines for $4,500. One inquiry came back. A used equipment dealer offered $2,800 scrap value for the iron. The machine that had survived the Depression and 2 wars faced execution by economic irrelevance. Tom, 19 and working summers in the shop, challenged his father with calculations scrawled on notebook paper. Annual revenue from the Cincinnati in 1981 had reached $47,000. Operating costs totaled $8,200. Net contribution of $38,800 represented an infinite return on sunk cost because the machine carried no debt. Even if they bought a CNC for production work, keeping the Cincinnati cost nothing except floor space. The machine stayed. The survival strategy emerged accidentally over the next decade. The shop discovered the Cincinnati excelled at operations where its supposed limitations became advantages. One-off prototyping required no programming time. A skilled operator could make a single, complex part faster manually than someone could write and debug CNC code. Large, heavy workpieces that wouldn't fit in standard CNC work envelopes sat comfortably on the Cincinnati's massive table. Interrupted cuts in hard materials, operations that destroyed expensive carbide tooling in automated machines, suited manual machining where operators could feel when cutting forces built dangerously and back off before breaking tools. Tom showed Chen the current job ticket, a $4,200 prototype die for an electric vehicle manufacturer. Engineering had sent a CAD model. Tom's machinist would complete it in 14 hours. CNC shops had quoted $6,800 because setup complexity exceeded cutting time. The Cincinnati's simplicity, once considered a fatal weakness, had become its primary competitive advantage in a market that valued speed over flexibility. October 2008, the financial crisis hit manufacturing like a physical blow. Whitmore Tool & Die's revenue collapsed 71% in 6 months. Banks demanded asset liquidation. The Cincinnati appraised at $8,500. Tom, 45 and running the shop after his father's retirement, opened the 1931 logbook to his great-grandfather's first entry. The handwriting remained crisp despite 77 years, fountain pen ink preserved under decades of careful handling. Purchased Cincinnati No. 2, serial 24487, $1,947. This machine will outlast me if I care for it properly. Tom made a decision that defied conventional business logic. He stopped taking salary, kept the one employee who understood the Cincinnati, and survived on the machine's earnings until the economy recovered. The mathematics of survival appeared stark in 2009 records. Revenue of $89,000 against costs of $14,200 generated net contribution of $74,800. This kept the lights on while the CNCs sat idle. No one wanted production runs during the crisis, but engineers still needed prototypes. The Cincinnati stayed busy because it carried no loan payment, required no monthly obligation whether it ran or not. David joined the shop in 2015, fresh from engineering school, fluent in SolidWorks and parametric design. He looked at the Cincinnati with the same skepticism his grandfather had shown in 1978. A new Haas 5-axis machining center would increase capacity 300%, enable lights-out operation, attract contracts requiring simultaneous machining. The business case appeared irrefutable except for one detail. It required scrapping the Cincinnati and laying off Bernard Kowalski, the 58-year-old machinist who had run that specific machine for 31 years. Tom took David to the machine. "Run a part, any part." David struggled for 45 minutes, producing work 8/1000ths over size. Bernard stepped in. Same part, 12 minutes within 3/10,000ths. Tom's point landed with precision that matched the finished component. The machine contained 94 years of accumulated knowledge. Bernard held 31 of those years in practiced hands. When you bought a new CNC, you received a manual. When you inherited Cincinnati, you inherited a century of solved problems. Tom walked to the machine and rested his hand on the column, feeling the faint vibration of the spindle through cast iron that had absorbed nearly a century of cutting forces. "My great-grandfather bought this machine in 1931 for $1,947, as he said, his voice carrying the weight of 4 generations. He's been dead for 43 years, but his handwriting is still in the logbook. The machine he chose is still making the parts that feed my family. That's not nostalgia. That's not romance. That's engineering wisdom. The understanding that the best machine isn't the fastest or the newest. It's the one that's still working when the loan's paid off, when the operator retires, when the economy crashes, when the technology shifts. It's the one that teaches you something every time you use it." He glanced at the serial number plate mounted on the column, its brass surface worn smooth by decades of passing hands. "Cincinnati Milling Machine Company, number 2, serial 24487, 1931. Still cutting, still teaching, still working."